Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. Today, 4th of May, 2025 years, and this is the ninth lectures of Advanced Artificial Intelligence, prepared for a course of master degree for students of software departments. And today we'll focus about the chapter 6 from these textbooks, and its topic, knowledge representation. The knowledge represents the second part of the second main part of the artificial intelligence, and focus about representing things to be saved in the computer and manipulated in the artificial intelligence by searching algorithm. The main topics of the knowledge representations focus about the concepts. When someone thinking about something, these somethings called objects, and these objects represented in mind by concepts. And these concepts represent all things about these objects. And when we thinking about another things, these second things also represented by concepts in mind. And so on. And all these concepts will be connected together to represent the thoughts of mind. And the representation of these concepts, or the structures of these concepts, how it's connected together, we may use semantic network, for example, about this representation. A semantic network consists of two parts. The first part, the nodes, and the other part, or the second part, represented by arc. Arc represents the connection between these nodes, and this node represents the concept in the mind. And arc labeled by meaning of these concepts to making the meaning or the explanation of the concept in mind. For example, when you want to thinking about statement, for example, Sarah, and the object, this object is Sarah, and the verb, for example, eat, and the subject is sandwich. When we represent these statements, we put Sarah in circular, the present node, and its object, and the other object is sandwich, and the verb is eating. Now, these two objects, sandwich and Sarah, represented by circular of nodes, two nodes, and connected by the verb. Now, this arc called verb eating. And now the eat represents the meaning of these two objects. Now the concept, this concept, representing the concepts of Sarah and sandwich, where they eat where she eat sandwich. This is simple examples about the representation of knowledge by using semantic network. Now let's continue on this chapter. Now, association theories. The association represents the connection between these concepts. Association represented by the correlation or relation between the concepts and the mind. Logical representation grow out of the efforts of philosophical and mathematicians to characterize the principles of correct reasoning. And the major concept of logic is development of the formal representation language with the sound and complete inference rules. Now we focus about the which rules, which language will be used to representation or for the representation of the knowledge in the mind or in the computer, because the mind, I mean the mind in the human and the machines, we mean by the mind by the computer. An alternative lines of the research has growth out of the efforts psychological linguistics to characterize the nature of human understanding. And there are many problems that arise mapping common sense reasoning into formal logic. For example, it is common to thinking of the operator, this operator, the and operator reply, corresponding to the English or and if then for. However, these operators in logic are concerned solely with the truth values and ignore the fact that the English if then suggests specific relationship or correlation or causal between its premise and its conclusion. Now this is word in English. Maybe someone will read this English, this word English or the statement in the English, maybe represent these two symbols as like this only two relation between two things or two words. But in logic, we see this on another view. We see this as truth value. When we see imply or the symbol of the or, we see statements in the view of the logics by truth value. This results either true or false. For example, the sentence, if a bird is cardinal, then it is red. Now the associating between bird cardinal with the color red. Now these two objects, the color and the bird, and the relation between them called association. And when we heard about the color red, we will remember the cardinal bird. Or when we someone talking about the birds and mention the bird of cardinal, we will remember the color or red color. That means the red and the cardinal, there is some relation between them. When we remember one of them, because the relation between them, we will remember the other. This is association. This is can be written in predicate calculus by for all x, cardinal x imply red x. That's mean, and this is really an English word, that means the x will be cardinal if it is color red, or when it's color red, this means cardinal. This may be changed through the series of the truth presenting operations into the logically equivalent expressions. For example, this is other word or the represented by the other formula or the expression for all x not red x imply that's mean not cardinal x. Or this is read in English language, if x is not cardinal, this is certainly will be not red. These two expressions have the same truth value. The two expressions, this one and this one, have the same truth value. That means when this is true, this is true. Or, for example, when we something, we mean x, if you can red, that means x is part of cardinal. Or if this something's objects, for example, x objects, if these objects not red, That means not cardinal. This is in the logic is equivalent. And the truth value is the equivalent and the same value, have the same value and truth value. But logically, or in the real life, this is confusing. Because X may be paper. If X white paper, that means X not red. Or the X here white, this is not mean cardinal. But if the color of the paper red, in this language or in this fashion, will be focused about the certainty that this X circled by paper, that's mean paper, maple imply this paper is cardinal. But it really is impossible. But logically it's true. This is the difference between logically and the real life, the representation of the real life. And these samples must be solved. This manner of the representation, because we use the predicate calculus for to representing the these two subjects and the concepts of the bird and the color. And this relation, this representation fallen in the mistake. And this is example for the paper. If the paper is red, are this paper is or is this paper is cardinal? Logically true. Will we say that the paper is the bird or the cardinal bird? And I must solve this problem. I solve this problem by using the semantic network and make the more explanation or more discussion and labeling to make the sentence have more meaning. However, truth value equivalence is appropriate in this situation. If we were to look for physical evidence of the truth of these statements, the fact that this sheet of paper is not red and also not cardinal is evidence for the truth of this expression, because the two expressions are logically equivalent. It follows that it is also evidence for the truth of the first statement. This leads to conclusion that the whiteness of the sheets of paper is evidence that cardinals are red. This line of reasoning strikes us as meaningless and rather silly. The reason for this ignority is that logical implications only expresses a relationship between the truth values of its operands, while the English sentence implies a positive correlation between memberships in a class and the positions of the properties of that class. In fact, the genetic makeup of birds causes it to have certain color. These relations are lost in the second version of the expressions. Also, the fact that the paper is not red is consistent with the truth of the both sentences. It is relevant to the causal nature of the color of birds. Now, the definition of the association. The association theory is following the empiricist traditions in philosophy define the meaning of objects in terms of a network's association with the other objects. And we use the semantic network or the network, and network consists of nodes, and these nodes connected by arcs, and the arcs represent the association or the relationship between these objects. And after I completing the completion between these objects, I get the complete meaning of the concepts. For the associations, when human perceive an object, that perception is first married into a concept, and this concept is part of our entire knowledge of the world and is connected through appropriate relationship to other concepts. These relationships form an understanding of the properties and behavior of the objects such as known. Because after this connection, the structure of these concepts, after using the nodes connected by the arc, I get figure as like the snow. For example, through experiences we associate the concept snow with the other concepts such as cold, white, snowman, slippery, and ice. Our understanding of snow and the truth of the statement such as snow is white and the snowman is white, the manifest itself out of this network of association. This is the concept of the ice. The concept consists of many objects, as like the snow, snowman, and other examples, the word of the cold. All these belong to the concepts of the ice, of the cold. There is psychological evidence that additions to the ability to associate concepts to humans also organize their knowledge hierarchically with information set at the highest appropriate levels of the taxonomy. In addition to the representation by using the networks, I will use another word. This word represents the hierarchy of the arranging the object inside this graph, and this ordering representing the order of the concepts or the time used to arriving the concepts, because the arrangement will be affect the time of accessing these concepts or this object in the concepts. Collins and Williams at 1969 modeled human information storage and management using a semantic network. It's like this. This is called semantic network. Semantic network consists of the objects. These objects, canary, ostrich, or the bird, or the animal, are connected by the sign yellow, fly, or. In this fashion, for example, when we say about the canary can sing or sing, or canary is yellow. This network can make or present the concept of the canary is yellow, and this is suitable for the representation of the concept of the canary is yellow. And in the same thing, in this manner, we can say that canary have or can fly. Canary can fly. But the time of the arriving these concepts of canary is a bird, then bird can fly, this is longer time than the concept of the canary is yellow. And this hierarchy will be used to making the and this arrangement will determine the time of arriving this concept, because this is first level and this is second level. Canary is 0. This is faster than defining the canary is or can fly, because can fly must arrive to the bird. Therefore, canary is a bird, and then bird can fly. Now this is figure representing the time of arriving the statement. For example, this is representing the time, and this represents the complexity. For example, the time of a canary can sing, and the time of a canary can fly, the time is longer than time of a canary can sing. And a canary has skin. It will take more time than the other, because canary in this level to arrive skin must visiting bird. Canary is a bird. Then bird is an animal. This is 2 levels. This first level, second level, third level, and then get the skin. This is more time than the other. Thus, this hierarchy will be used to determine the time needed to arrive the real concept. The structure of this hierarchy was derived from laboratory testings of human subjects. The subjects were asked questions about different properties of the bird, such as, for example, this is a canary a bird? Canary is a bird. Can a canary sing? Or can canary fly? Canary can fly. This is sing, and canary can fly. As obvious as the answers to these questions may seem, reaction times studies indicated that it took longer for subject to answer can canary fly than it did to answer can canary sing. Collins and Williams explained these differences in response times by arguing that people Collins and Williams explained this difference in the response times by arguing that people store information at its most abstract level. Instead of trying to recall the canary's fly and robin's fly and swallow's fly, all stored with the individual birds, humans remember that canaries are birds, and that birds have usually the property of the flying. Thus, these structures of the network maybe assist us to using the objects that contains all the features of the particular objects. For example, in the bird they have features all the canary, ostrich, and robins, and so on. Thus, in the other important things in using the network or the semantic network, it can get us the meaning of the objects containing multiple features in the one object, and this object will be connected or be shared by the other objects belong to these objects. For example, the objects of the birds consist of the canary, of the robins or swallows, or the cardinal. All these are birds. These concepts is named the inheritance, and we'll introduce the concept of the inheritance. This is the main concept of the object-oriented language, using the inheritance when we creating objects or the class, and then we create another objects. It's called initialization or instance, and this object represents the instance of the main class, and this instance sharing the properties of the main class. For example, bird contains skin or contain wings, and its features fly, and its feature has feathers. All these features will be inherited to the objects that created to the bird. For example, the canary. Canary's objects is created from the main class bird, and bird inherited its classes to the canary, or sharing its classes or its features to the canary, and birds inherits and sharing its features to the ostrich. Thus, canary has our camouflage, and all these camouflage. These features will be shared to the object that belong to the main class. This is called inheritance. Now, this inheritance, even marginal properties such as eating, breathing, and moving are stored at the animal's levels. So trying to recall whether a canary can breathe or should be take longer than recalling whether canary can fly. This is of course because of the human must travel further up the hierarchy of memory structure to get the answer. Now, the inheritance systems allow us to store information at the highest levels of the abstractions, which reduces the size of the knowledge base and help prevent update inconsistency. For example, if we are building a knowledge base about birds, when we building knowledge base about the birds, we can define the traits common to all birds, such as flying or having feather for the general class birds, and allow particular species of bird to inherit these properties. This reduces the size of the knowledge base by requiring us to define these essential traits only once, rather than requiring their assertion for every individual. This will be used or be suitable for reducing the time and the size. Inheritance also helps us to maintain the consistency of the knowledge base when adding new class and individual. As like the object-oriented language, when we create a class and there reinitiates or the assigning for instancing some other object to this main class. It seems that we are adding the species robins to an existing knowledge base when we assert that robins is subclass of songbird. Robin inherits all of the common properties of the both songbirds and birds. Now, a semantic network represents knowledge as a graph with the nodes corresponding to the facts or concepts, and the arc relations or associations between concepts. Both nodes and links are generally labeled. For example, the semantic network that defines the properties of the snow and ice appears in figure 7.2. Now, when we reach defining the concepts of the snow, temperature, cold, this figure will get us this meaning. And if we want to introduce now we will use this figure to introduce or to explain the meaning of these concepts of the snow, snow texture, silver, or snow, or the hardness of the snow is soft. By the snow, hardness soft, or ice, form of water, and this figure represents the representation of the knowledge base about the snowman or the frosty, the class frosty, and initiated instance of snowman. Snowman is this class of frosty, and the snow is the class of snowman. This network could be used to answer a range of questions about snow, ice, and snowman. Now, when asking about the snowman or the snow or the ice, this network will give us any questions about answering about these objects. These inferences are made by following the links to related concepts. Semantic networks also implemented inheritance. For example, Frosty inherits all the properties of the snowman. Tocqueville's early work established most of these significant features of the semantic network formalism, such as labeled arcs and links, hierarchical inheritance, and inferences along association lists. It provides limited in its ability to deal with the complexities of many domains. One of the main reasons for this failure was the poverty of relationships, that mean links, that capture the deeper semantic aspect of the knowledge. And most of these representation extremely general associations between nodes and provided no real basis for structuring of semantic relationships. The same problem is countered in the effort to use predicate calculus to capture semantic meaning. Now we will talk about the topics of the early works in the semantic networks. At 1973, Simons focused on the case structure of the English verbs. Links define the roles played by the nouns and the noun phrases in the actions of the sentence. Case relationships include agents, object, instrument, locations, and time. A sentence is represented as the verb node with the various case links to nodes representing other participants in the action. This structure is called a case frame. In parsing sentence, the program finds the verb and retrieves the case frame for that verb from its knowledge base. It then binds the values of the agents, objects, etc. to appropriate nodes in the case frame. We will take some examples about the sentence. For example, let's the sentence, Sarah fixed the chair with the glue. This is example, Sarah fixed the chair with the glue, might be represented by the network in the figure below. Look at this figure. This is Sarah, and known by the agent, and the relations between Sarah and chair, for example. This is the relation is fixing, and chair is object, and the time is past, and the instrument used to the fixing the chair is the glue. Now this network representing the whole meaning of this concept. The concept now in my mind, when we ask me anything about the Sarah and the chair and the operations that performed by Sarah at the chair, I can answering any questions may be asked me. For example, which the instrument can be used, which instruments used by Sarah? Glue, because this is Sarah and the fixing between glue and Sarah and this instrument. And if we asking which objects or which things fixed by Sarah? Chair, because this is fixing between agent Sarah and the object is chair. Now the chair fixed by Sarah and the instrument is glue. And in which time? In the past time. Where in the individual sentence parsing these built-in relationships and indicating that Sarah is the person doing the fixing and that glue is used to put the chair together. This figure can get this meaning of the parsing. That Sarah is the person doing the fixing and the glue is used to put the chairs together. And the most ambitious attempts to model formally the deep semantic structure natural language, program and conceptual dependency theory. Thus, the conceptual dependency theory offers a set of 4 primitive conceptualization from which the world of the meaning is built. These are equal and independent. This is 4 primitives. First one, ACTS, represent actions. The second, PPS, object that represents picture, producer. And AIS, modifier for action aiders. And PA, modifier for objects, represent picture and aider. And this in this language, we need objects and we need action, and this action about these objects, this is modifying as action, or this is modifier, or this is modifying. because the actions and objects, because we may have two objects and one actions. Which action caused the other things? For example, object 1, eating or eat, object 2. Now, the eat represents action. And two objects, for example, Ali eats sandwich. Now two objects, Ali and sandwich. The action is eats. And the modifier, which actions is either, and which action is eaten, for example. Who's eating and who's eaten. These four objects or four primitives can be used to illustrate all ambiguities in the language when they represent the language. For another example, where we heard in that dog bites Ahmed. Which one bites the other? Dog bite Ahmed or Ahmed bite the dog? In this fashion, we will represent this in simpler manner. Okay? For example, all the actions are assumed to reduce the one or more of the primitive A, C, T, S. For example, trans is used for transfer relationships. For example, give used for the trans. And the primitive PTRANS, transfer physical location of an object. For example, go. When we use the word go, that's mean moving physical object to another location. Physical objects. And propel, apply. حبيبي دكتور ممنون دكتور. Propel apply physical force to an object, for example, push. Add move body part by Auna, as like kick. When Ahmed kicked the ball or kicks ball. Grab an object by an actor. For example, grass like this. Ingest, for example, injects an object by animal eating. And expiration. Now this is when represented the main thing that we use in the semantic network. First, conceptual dependence in the figure 7.6 describes the relationship between a subject and its verb. And third describes the verb-object relationship. And these can be obtained in the presented as simple transitive sentence, such as John throws the ball. For example, these objects, PP, to supply or to actor, acts indicates that an actor acts. And PP, this symbol and PA, indicates that an object has certain attributes. And action, apply, PP, and this action labeled by the O indicate the object of an action, and so on. In this conceptual dependency, representation of the sentence John throw the ball. Now this is represented by these objects. The relation between John and Paul is proper, and ball and John is represented by objects. Now we will use symbols. For example, the symbol of P represents is the past time, and F future time. T represented the transition operation, and K representing the continuing process, and TS representing the start time of the transition, and question mark interrogative, and TF representing the finish time of the transition, and C represents conditional part, and slash represented the negation of the sentence, and note represents the present time, and delta question mark that represents timeless, and so on. For example, John ran. John ran, the first statement, can be represented by the PP and the symbol two arcs, two direction, and can be represented by John and represented by up, and so on. This is representing some basic conceptual and dependencies and their use of the representing more complex English sentences. And this is adapted for the Shanks and Gold. Now, in this figure 7.10 or 7.9, is represent conceptual dependency. It is representing John ate the egg. John ate the egg, and the type of the operation is ingestion or ingestion. And this is represented P, and this is represented object. And this figure 7.10, conceptual dependency representation of the sentence John preventing Mary from giving a book to Bill. Now, this sentence or this figure indicates the direction of the dependency, and Toro indicates the agent verb relationship, and B indicates the past tense, and ingest is the primitive acts the theory, and O object relations, and D indicates the direction of the object and the action. Now the other topics of the scripts. Scripts is structured representation describing a stereotypes sequence Now, script is structured representation describing a stereotype sequence of events in the particular context. The script was originally designed by the Shanks and his research groups as a means of organizing conceptual dependency structures into the description of typical situations. Scripts are used in natural language understanding systems to organize knowledge base to catch all these situations that the system is to understand. The components of the scripts are two components. The first one, entry conditions or descriptors of the word that must true for the secret of the code to be called. In our example, secret these include an open state someone and restaurant. هلا دكتور في ساعة هسه دقائق ان شاء الله ان شاء الله ان شاء الله حياك دكتور of restaurants and hungry customers that has some money. Now, the scripts are used in the natural language understanding systems to organize knowledge base of the situations that the system is to understand. The other things, the results or facts that are the truth once the script has terminated. For example, customer is full and poorer. The restaurant's owner has more money. The third thing, proofs or things that support the content of the scripts. These will include tables, waiter, and menu. The sets of proofs support reasonable default assumptions for both the situation and the result. And the fourth, roles are the actions that the individual participant performs. For example, the waiter takes orders, delivers food, and presents the bill, and the customer's orders, and so on. And finally, the person or the customer will pay its money. And the fifth thing is sense. Sense breaks the scripts into sequence of sense, each of which presents temporal aspect of the scripts. In these restaurants, there is entering, ordering, eating. This is sense. And this figure represented the whole representations by using the scripts. This is representing the operation or the concept of entering the customers into the restaurant for ordering the particular menu to eating something. Now the conceptual graph. Conceptual graph is a finite connected separate graph. The nodes of the graphs are either concepts or conceptual relation. Conceptual graphs do not use labeled arcs, not like the semantic network using labeled arc. Instead, it used the conceptual relations node, the present relations between concepts. Because conceptual graphs are separate, concepts only have arc to relations and vice versa. Now this figure 7.14, dog and brown are concepts nodes and color conceptual relations. To describe these types of nodes, we represent concept as boxes and conceptual relation as ellipses. Conceptual graphs, concepts node represent either concrete or abstract object in the world of this course. Concrete concepts such as cat, telephone, restaurant. And abstract concepts include love, beauty, loyalty, and so on. Now, these two objects represented by concrete concepts and abstract concepts. Relations of RTN is represented by conceptual relations node having n arcs as shown in figure 7.14. For example, book, when a rope, or flies. Dog has color brown. child, its parents, father and mother. This is more than one arc. And figure 7.15 is the graph of somewhat greater complexity that represents the sentence. Mary gave John the book. Now, Mary and John, and this object transfer between them is the book. Now represented by the person one, Mary, the person two is John. This is represented the agent, and this receives that's receiving the something, and the object between them, or the operation between them, or action is give, and the object that's giving for the other one, this book, and it's called object. Now the types and individuals and names. For example, dog Emma, its color brown. This conceptual graph indicating that the dog named Emma is brown. And this conceptual graph indicating that particular but unnamed dog is brown. This is name, Emma, but in this not particular dog. But this is dog is called Emma. This is more special than this. And this graph, conceptual graph indicating that a dog named Emma. Now, this special and this global. And this representing the special and the global. And assigning the global to its special called Emma. In other words, this word represented the statement focused about dog called Emma, and this not focused on particular dog. Any dog is brown, and these, after we connected these two words together, or these two figures together, we get that particular dog for whole dogs dog named Emma. Now may have a person with more than one names, and this figure conceptual graph of person with the three names, and this person hash number. The first name is Lil, and the second name is MG Joe, and this here Nancy. Now we can use this figure or the secret to producing or the definitions or assigning more than one name for the particular object. Now the genetic marker star represented or used to indicate an unspecified individual. These are represented by the asterisk followed by the variable. For example, star X and star foo. This is useful of two separate nodes to indicate the same but unspecified individual. Now this generalization of this and the specialization is like this. This is figure 7.22. This is examples of restrict, joins, and simplify operation. لسه صار بس ما شاء الله شو احنا بدينا 10 اعتقد هو ان هي لهنا لان هذا الموضوع هو نفس المكرر بالثانيه ان شاء الله.